not remember being on this side of the screen, but that's okay. That's the side. Yeah, I have. I don't know what's gotten into me. Anyway, I am glad that everyone's here. I'm here. Sorry for the super late start. When I woke up this morning, man, I really just wanted to stay in bed. I really did not want to study. I'm not gonna lie. And then I came into my office, and the cats had some accidents. A lot of accidents had happened in my office, which just made me want to not do it even more. But as my old man once said, being a man means you do things that you don't necessarily want to do because you know you got to do them. So that's how you find consistency in life, is that you just push through when you don't want to do it. So although I'm late, I am here, and we're going to do this. We are going to do day 12 of the Jeremy's Tech Lab. If you have not already, make sure that you subscribe to his channel. He is absolutely phenomenal. If you haven't already, you should definitely subscribe to me so that way you don't miss out on further streams. Okay, and if you're watching on ParaDiddlePete, you should come on over to my other channel with Tyler Lamond, where I have a bunch of network stuff and like tech stuff and things to prepare you for studying. The link to that channel is in the description. So, but other than that, we're going to get started. We're going to get working on this one. We do have a packet tracer over here. We will watch this on probably, I don't know. No one really complains when I put it at 1.5 speed. So that's what we're going to do. Let's get started.
Welcome to Jeremy's IT Lab. This is a free complete course for the CCNA.
Jeremy,
if you like these videos, please subscribe to follow along with the series.
Animal.
Also, please like and leave a comment and share the video to help spread this free series of videos.
Yes.
Thanks for your help.
Yes, go out,
This video,
share.
unlike the last one, is not going to be practical, meaning that you won't actually go on and configure a Cisco router or switch.
Ah, crap.
Also, most of the information in this video won't be new. We've already covered most of it in previous videos. However, I decided to make this video because I think it's very important to make sure you have a good understanding of the complete process a packet goes through when being sent across networks.
I also already
Hopefully,
have my tea.
This video will be a little shorter than the usual ones. Let's get started. So, what will we cover in this video?
20-minute video.
We'll cover the entire process of sending a packet to a remote destination. This will include things like ARP, encapsulation, de-encapsulation, etc. Of course, there are different levels of depth we can go into when talking about this process, and I won't give unnecessary details that would only be expected of a CCNP or CCIE. But in this video, I hope to give you a solid understanding to get you ready for your CCNA. My hope is that this video will help you put all of the pieces together that we learned previously. So this is the life of a packet, the process a packet goes through when being sent to remote networks. Here's the network topology we'll use for this video.
Okay.
If you watched day 11's video, you should recognize this topology, as it's the same one we used to demonstrate static routing. We'll follow a packet being sent from PC1 in the 192.168.1.0/24 network to PC4 in the 192.168.4.0/24 network. Let's assume we have pre-configured static routes on these devices, so that the packet will follow the same path as in the static routing video. That is from PC1 to R1, R2, R4, and then PC4. This doesn't have to be the path the packet takes. The path that goes via R3 instead of R2 is valid too, but we'll stick to the same path as last time.
Okay.
Now, since we're not just looking at layer 3 in this video, let me add MAC addresses for these devices. I'll use 1111 for PC1. Now, as you know, a MAC address is actually 12 hexadecimal characters, but just to save space, I'll shorten them to 4. R1's G02 interface has a MAC address of AAAA, and its G00 interface has a MAC address of BBBB. That's something I didn't mention before. Each interface on a network device has a unique MAC address.
Whoa.
Note that switch 1's interfaces also have...
So a router, man, that's crazy, because like a switch only has one. A switch only has one IP address and one MAC address. It just has a bunch of ports where it can just like push things out of, or I guess interfaces. I need to stop saying the word port. But that's okay. That's interesting, because I was also under the impression that a MAC address was a physical address that was given to a physical device and it was burned in. I know you can spoof them, but that means that each interface has that. So a router's like a lot of things. That's kind of intense.
MAC addresses. However, for this video, it's not necessary to know the MAC addresses of the switches. So to avoid clutter, I'll leave them out of this diagram. R2 has a MAC address of CCCC on its G00 interface, and DDDD on its... It's not necessary to know the... That's address of, but just to save space, I'll shorten them to 4. R1's G02 interface has a MAC address of AAAA, and its G00 interface has a MAC address of BBBB. That's something I didn't mention before. Each interface on a network device has a unique MAC address. Note that switch 1's interfaces also have MAC addresses. However, for this video, it's not necessary to know the MAC addresses of the...
Whoa, so the switch, that they have MAC address, or is it because it's just the gigabyte? That's something to look up later.
Switches. So to avoid clutter, I'll leave them out of this diagram. R2 has a MAC address of CCCC on its G00 interface, and DDDD on its G01 interface. R4 has a MAC address of EEEE on its G01 interface, and FFFE on its G02 interface. I didn't make it all Fs because the MAC address of FFFF, 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 12 Fs, is the broadcast MAC address. So just to avoid confusion, I added that E on the end. Finally, PC4 has a MAC address of 4444. Okay, so PC1 wants to send some data to PC4, and it's encapsulated in this IP header. The source is 192.168.1.1, PC1's IP address, and the destination is 192.168.4.1, PC4's IP address. Now, because PC1's IP address is in the 192.168.1.0/24 network, it notices that the address 192.168.4.1 is in a different network. So it knows that it needs to send the packet to its default gateway, which is R1, something we have already pre-configured. However, in this example, PC1 has not sent any traffic yet, so it needs to use ARP, the address resolution protocol, something we covered in a previous video. Let's look at the ARP process once more. So, PC1 makes this ARP request packet. The source IP is its own IP address, and the destination is R1's G02 interface, which is the default gateway configured on PC1. Next is the MAC addresses. This is a minor point, but note that I put the source IP before the destination IP, but the destination MAC before the source MAC. That's because in the IPv4 header, the source IP address comes first, but in the Ethernet header, the destination MAC address comes first. Anyway, just a minor point. The destination MAC address is the broadcast MAC address of all Fs, because it doesn't know the MAC address of R1, so it will send the frame to all hosts on the network. Finally, the source MAC address is its own MAC address. So, it sends the frame, which switch 1 receives and broadcasts out of all its interfaces, except the one it received the frame on. In this example, only PC1 and R1 are connected to switch 1, so that means that switch 1 will forward the frame out of its G00 interface. To translate the meaning of this frame into English, PC1 is basically saying, "Hi, 192.168.1.254, what's your MAC address?" Although I'm not going to really talk about the switches much in this video, note that switch 1 learns PC1's MAC address on its G01 interface when the frame arrives on its G01 interface. ARP table. When this broadcast frame arrives in R1, it notices that the destination IP is its own IP, so it creates this ARP reply frame to send back to PC1. Although the ARP request message was broadcast, because R1 learned PC1's IP and MAC addresses from the ARP request message, the ARP reply can be sent unicast directly to PC1. So that's what R1 does. To translate this ARP reply message into English, basically it means, "Hi 192.168.1.1, this is 192.168.1.254. My MAC address is AAAA. Note that switch 1 will learn R1's MAC address from this message when the frame arrives on its G00 interface. So, now PC1 knows the MAC address of its default gateway, so it encapsulates the packet with this Ethernet header. Keep in mind, the original packet is not changed. The destination address remains PC4's IP address, not R1's IP address. Only at layer 2 is the destination set to R1's MAC address. So, it sends the frame to R1. R1 receives it and removes the Ethernet header. It looks up the destination in its routing table. The most specific match is this entry for the 192.168.
Okay. Hold on. I need a second to process that. Because, okay, so one of the things I have a hard time grappling with.
Hi, bro.
Hey, what's up, man? One of the things I have a hard time grappling with is why do we have IP addresses and MAC addresses? Why can't we just have one? I know that seems like a really dumb question to ask.
I am, sir.
That's good. I'm glad you're doing well, man. So this PC1 is trying to get to PC4, but it has to find its default gateway. Should already know its default gateway. And it's looking for its ARP because it needs to know its ARP.
Ma'am, I am, sir.
Oh, sir. Are you, sir? Hey, actually, I used to work with a guy who was a knight. He had been knighted, and his name was, it was actually kind of funny. His last name was Pope. So he was Sir Pope. I thought it was kind of funny. So back to the task at hand here.
Ronak Varma.
Look, I see your name. Ronka. Look, I know I'm butchering that. I know that I'm not saying that correctly. I apologize. I'm terrible with names. So we have PC1 goes to R1. But when it said that it went from PC1 to R1, it had a different destination. So are there different packets with different headers that have... They would all have this...
I will manage.
No, because the original source MAC address, the original source was this. Okay, PC1 wants to send it to this. It recognizes that it's not in the network, so therefore it's looking for the default gateway. Because if it's trying to send a message or packet or whatever you want to call it, it's trying to reach a device that is outside of the network, it knows that it has to go to the default gateway. So now the packet...
You are teaching or learning?
I'm doing both, man. I'm studying for the CCNA, and there's just a lot of things that, like, I think I understand. There's a lot of things that I do understand. So, like, this is just me going through it. In all reality, the reason I'm streaming this is to hold me accountable to actually studying. Otherwise, I'll talk myself out of it, and I'll say that I don't need to. CCNA is a lab. They're not a lab. It is a certification that you can get to be able to, for networking, for like the internet, for routers, switches, internet phones, for IT work. Yeah. I think it stands for... Crap, what does it stand for? I should know this. What does CCNA stand?
Is this related to cybersecurity?
Yeah, absolutely it is. Yeah, okay, Cisco Certified Network Associate. Yeah, there's some security that goes with it. I would say that people in cybersecurity probably maybe not have a CCNA, but they know a lot about networking.
I am learning this.
Nice. Let's continue with the video.
4.0/24 network, which specifies a next hop of 192.168.12.2. So, R1 will have to encapsulate this packet with an Ethernet frame with the appropriate MAC address for 192.168.12.2. However, R1 doesn't know R2's MAC address yet.
Okay, so I know this is going beyond the scope of this lesson, but I think I finally am able to put into words what I get confused with and how it boggles my mind. Okay? How does this router know where this PC is? There's no way it can know that. Especially if it's never contacted it. So how does it know the shortest path to this PC? That's what gets me. And I know that's a completely different protocol. That's a totally different day that we're gonna like conquer that stuff. But I think that's what always, like, as I've never been able to fully put it into words.
You.
No, dude, you're fine. Don't worry about it, man. Like, I love chatters. I was also a school teacher for a long time, so I'm used to like trying to do something and then having people like talk to me and then still being able to do the thing. So we have the PC1 here that's trying to talk to this. It doesn't know where PC4 is. So it's going to talk to...
And sorry, bro, my English not straight.
That's fine. I worked at a very diverse high school, my last teaching job, so I was very used to it. PC1 does... all PC1 knows is that PC4 is not in the network. So its protocols that it sends it to the default gateway. But the router doesn't have a protocol to be like, oh, what? You know what I'm saying? I mean, I guess there are protocols. But anyway, that is the part that I am confused on.
So how will it learn R2's MAC address? It will use ARP, of course. The source IP address of this ARP...
And we're just assuming that it already knows its path for this video. My question is, how does R1 know the path? How does it know its shortest path? I know it's a protocol. We'll cover it in a later video.
Request will be R1s, and the destination will be R2s. The destination MAC address is all Fs, the broadcast MAC address, because R1 doesn't know R2's MAC address, and the source is BBBB, which is the MAC address of R1's G00 interface. So it sends the ARP request, and R2 receives it. Basically,
Wait,
what this
so does that
I am your
mean...
new subscriber. I love your dedication.
Oh, thanks, dude. I appreciate it. Thanks for the sub. I really do. Thank you. So since it's a MAC address, so it's flooding it, right? So does that mean that it went to R3? Now, I understand that it's supposed to go to the shortest path possible, right? Or the most efficient path possible is probably a better terminology. But my question about it is, how did it know to take this path instead of this path? I know for the video, argument's sake, he said in the very beginning of the video, this is what we were going to do.
Cybersecurity.
In cybersecurity, this would be all networking. Because in cybersecurity, you deal with, you have to understand networks in order to put up firewalls and do all that stuff. I don't know a lot about cybersecurity yet. I'm still figuring all that stuff out. So the R1, how does it know to go to R2? Would it just decide? Would it be like, okay, there's these two paths and they're both equal, and it would just randomly pick?
this ARP request says is, hi, 192.168.12.2, what's your MAC address? R2 receives the broadcast, and since the destination IP address matches its own IP address, it makes this ARP reply to send to R1. Once again, because it learned the IP and MAC addresses of R1 from the ARP request, it doesn't have to broadcast the frame. So it sends this ARP reply back, which basically says...
So when it broadcasts this, it goes here, and then does this just broadcast it? Is it just a constant flood of broadcasting until it finds its destination, and then it comes back? And whichever one comes back the fastest means that that's the best route? That would make sense to me.
Hi, 192.168.12.1.
Okay,
This is
I stopped this a lot. We're going to kind of back it up just a little bit.
R1. R1 receives it and removes the Ethernet header. It looks up the destination in its routing table. The most specific match is this entry for the 192.168.4.0/24 network, which specifies a next hop of 192.168.12.2. So, R1 will have to encapsulate this packet with an Ethernet frame with the appropriate MAC address for 192.168.12.2. However, R1 doesn't know R2's MAC address yet. So, how will it learn R2's MAC address? It will use ARP, of course. The source IP address of this ARP request will be R1's, and the destination will be R2's. The destination MAC address is all Fs, the broadcast MAC address, because R1 doesn't know R2's MAC address, and the source is BBBB, which is the MAC address of R1's G00 interface.
I'll answer that question in a moment.
It sends the ARP request, and R2 receives it. Basically, what this ARP request says is, hi, 192.168.12.2, what's your MAC address? R2 receives the broadcast, and since the destination IP address matches its own IP address, it makes this ARP reply to send to R1.
And sends a unicast.
Once again, because it learned the IP and MAC addresses of R1 from the ARP request, it doesn't have to broadcast the frame. So it sends this ARP reply back, which basically says, hi, 192.168.12.1, this is 192.168.12.2. My MAC address is CCCC.
Okay.
Okay, now R1 knows R2's MAC address, so it can encapsulate the packet with an Ethernet header, inserting R2's MAC address in the destination field, and the MAC address of R1's G00 interface in the source field, and it sends it to R2.
Okay, so to answer your question, how much time this route will to reach the destination, we haven't covered that yet. We haven't talked about how to calculate that or anything like that, but you are correct. That is something that needs to be considered because of time to live. So that kind of goes outside the scope of this lesson. We'll get there though.
After receiving the frame, R2 removes the Ethernet header. R2 then looks up the destination IP address in its routing table, and the most specific match is this one for 192.168.4.0/24, with a next hop of 192.168.24.4. Although 192.168.24.0/24 is a connected network to R2, it doesn't know the MAC address of R4. So, you know what's next. R2 will use ARP to discover R4's MAC address. R2 prepares this ARP request frame, using its own IP and MAC addresses for the source, R4's IP address as the destination, and the broadcast MAC address, and it forwards it out of its G01 interface. With this ARP request, R2 is saying, hi, 192.168.24.4, what's your MAC address?
Okay, I have another
R4
question.
receives the broadcast, and since the destination IP address is its own, it creates this ARP reply frame to send back to R2. Once again, it already knows R2's IP and MAC addresses, because they were used as the source addresses for the ARP request. It sends the unicast frame back to R2.
Unicast.
With this ARP reply, R4 is saying, hi 192.168.24.2, this is 192.168.24.4. My MAC address is EEEE. Now that R2 knows R4's MAC address, it encapsulates PC1's packet with an Ethernet header with a destination MAC address of EEEE, which is R4's G01 interface, and a source MAC address of DDDD, which is R2's G01 interface.
Okay, so to clarify, like, because earlier I was talking about like how I have a hard time understanding like how R1 knows to talk to R2, like based off of the path, like the best path possible kind of thing. My frame of reference that I'm trying to grapple is like if I'm trying to contact someone in England. I've never emailed someone in England before. I've never tried to reach anybody from to England before. So then how would it know, right? But which I think I just kind of answered my own question in my head. I'll explain that in a second. But I think in this topology, in this diagram that we're looking at, it's way easier to look at it in terms of like an enterprise, just like a business or like a college. Like this is, let's say, the student center. And then this is the welding building or the facilities or, you know, like financial aid, something that's in a completely another building. I would set up the routers and the switches so that way it would know where to go. Now, I do think I just answered my own question. If I was trying to email or contact somebody in England, my information, my email would go to Google and then Google would figure it out, right? It just would so happen that okay, I'm kind of exploding my mind right now. Let's keep going.
4 receives the frame and removes the Ethernet header. It looks up 192.168.4.1 in its routing table, and the most specific match is this entry for 192.168.4.0/24, which is directly connected via the G02 interface. But once again, R4 doesn't know PC4's MAC address yet, so you know what it has to do next. It will use ARP to learn PC4's MAC address. It prepares this ARP request frame. Again, the source IP and MAC addresses are its own, the destination IP address is PC4's, and the destination MAC is the broadcast MAC address of all Fs. It sends this message out of its G02 interface, saying, hi 192.168.4.1, what's your MAC address? Note that switch 4 will learn R4's MAC address on its G00 interface from the source MAC address field of this Ethernet frame.
I know that I can talk
After PC4 receives the frame, it checks the destination IP address. Since it is its own IP address, it will send an ARP reply. The ARP reply will be unicast, using PC4's IP and MAC addresses for the source, and R4's IP and MAC addresses for the destination. It sends the frame out of its network interface, saying, hi 192.168.4.254, this is 192.168.4.1. My MAC address is 4444. Note that switch 4 learns PC4's MAC address when it arrives on its G01 interface. Now that R4 knows PC4's MAC address, it adds an Ethernet header to the packet, using its own MAC address on the G02 interface as the source address, and PC4's MAC address as the destination. R4 sends the frame to PC4, and finally it has reached its destination.
Okay, so let's look at this real quick. Okay. Why is... Oh, whoops. Let's get rid of that. Okay, so basically what's happening, if I'm understanding correctly, is that it's just a constant back and forth. This is sending an ARP request. Then it's sending it back. Then this is sending an ARP request. Then this is sending confirmation. Then this is sending an ARP request. And then it's sending it back. And then it's doing the same thing. Now, this one probably already has its MAC address, but if it didn't, it would also send it back. So I think that is essentially what's happening throughout everything. So let's assume that this is a college. College. No, we only need one L. No, no, you're bad at English. You won't understand the joke. I'll keep it correct. Okay, so college, and then that means that if this was like the marketing department and this was student affairs or registration or something, it would already have this path. It would already know this path. But if this was something different, when R1 is trying to find its next person, it's going to send it out on all Fs, which is going to be a broadcast. So it's going to go here, and it's going to go over here, and honestly, it's going to go anywhere else it's connected, until it finds the path that knows this IP address, in which case it'll send back and say, yes, that is me. Okay. Can we move this back now? Yeah. Okay.
Notice that the original packet hasn't changed
With that.
throughout the process. It's always used the same IP header with a source IP address of 192.168.1.1 and a destination IP address of 192.168.4.1. Also, notice that the switches didn't actually modify the frames at any point. The switches forwarded the frames and learned the MAC addresses, but they don't actually de-encapsulate and then re-encapsulate the packet with a new Ethernet header. Okay, now let's say PC4 sends a reply back to PC1, and we've configured static routes on the routers so that the traffic follows the same path on the way back to PC1, going via switch 4, R4, R2, R1, switch 1, and then reaching PC1. What will be different? First off, there will be one major difference. Since these devices have already gone through the ARP process, there won't be any need for ARP requests and replies.
Yeah,
the packet will simply be forwarded from device to device, being de-encapsulated and then re-encapsulated as it is received by and then forwarded by each router. So, that's it. Just a basic walkthrough of how a packet is forwarded between routers to pass it along to its final destination. Now, as for today's quiz, I'll do something different than usual.
Okay, that really cleared up a lot of things. It made me have a lot more questions, but I feel like my questions are more like guided. Like they're much more spearheaded. They're much more clear.
Instead of having multiple choice questions as usual, we'll use the same diagram to test your understanding. Let's get started with the quiz. Here's question 1. PC4 sends a packet to PC1. What is the destination MAC address when it is sent from PC4's network interface? Pause the video to think about your answer.
It would be FFFE.
The answer is FFFE,
Yes.
which is the MAC address of R4's G02 interface. That's because to send a packet to PC1, which is in a remote network, PC4 must send the packet to its default gateway, R4, first. To do that, it encapsulates the packet with an Ethernet header, with its default gateway's MAC address as the destination. Okay, let's go to question 2. PC4 sends a packet to PC1. What is the source MAC address when it is received on R1's G00 interface? Pause the video to think about your answer.
Okay, I missed the question. PC4 sends a packet to PC1. What is the source MAC address when received on R1's? The MAC address when received should be BBB. B. I missed a B.
The answer is CCCC, which is the MAC address of R2's G00 interface.
Oh, the source MAC address, not the destination.
When R2 sends the packet to R1 en route to its destination, PC1, it encapsulates the packet with an Ethernet header using its own MAC address as the source MAC address. Okay, let's go to question 3. PC4 sends a packet to PC1. What is the source MAC address when it is sent from switch 1's G01 interface? Pause the video to think about your answer.
Okay, so PC4 sending a packet to PC1. What is the source MAC address when it is sent from switch 1's? It would be AAAA, right? Now, he also said that switches have their own MAC addresses, but we didn't really cover that. He said he was going to cover that later. So based off the information that we have right now, it should be AAAA because it is the source MAC address.
The answer is AAAA,
Yep.
which is the MAC address of R1's G02 interface.
Bro,
Switch
what
1
is
doesn't
this
alter
on
the
top
frame
of
to use
your
its own
head?
MAC address. It simply forwards the frame out of the correct interface, or floods it if it doesn't know the destination.
What's on top of my head? No,
Let's go to
nothing.
question
I'm
4.
balding. That's what it is.
PC4 sends a packet to PC1. What is the destination IP address when it is sent from R4's G01 interface? Pause the video to...
PC4 sends a packet to PC1. What is the destination IP address when it is sent from R4's G1 interface. Well, it's sent from here. The destination MAC address should be
Not this, bro.
192.168.12.2. That's what it should be.
To think about your answer. The answer is 192.168.1.1, which is
Damn! How'd I get that wrong? What is the destination IP address when sent from R... Oh, damn it. Sent from R4s. So when it's sent from R4, it would be 192.168.30.20. So then why is it 1.1.1?
On the display like pink colored and yellow colored.
On the display. Are you talking about like that's like legitimately behind me? Or are you talking about like something that's on here? You talking about like that stuff? That's just a light. That's just an LED light. Actually, I should probably turn it off. I try to turn it off when I'm studying because I don't know, it doesn't set the vibe right. Anyway, how was this?
No bore. Bro.
Destination IP address. Oh, the destination IP address is going to be the PC because that's how we're getting somewhere. We're trying to find that place. Okay, I understand.
The answer is 192.168.1.1, which is the IP address of PC1. Although each router modifies the source and destination MAC addresses in the Ethernet header as it forwards the packet, they don't modify the original packet itself, so the destination IP address won't change.
Oh, are you talking about this thing that's over here? That's the packet tracer. That's what we're going to do in a second.
Since PC4 is sending the packet to PC1, that means the destination will be PC1's IP address, 192.168.1.1. Let's go to question 5.
I am watching that
PC4 sends a packet to PC1. What is the source IP address when it is received on R1's G00 interface? Pause the video to think about your answer.
Okay, PC4 sends a packet to PC1. What is the source IP address when it is received on R1's G? So what is the source IP address? So the source IP address when it hits here should be 192.168.12.2. Yeah, this is a packet tracer. We're gonna do this right after this video.
The answer is 192.168.4.1, which is the IP address of PC4. As I said in the last question, the original packet is not modified as the routers forward it to its destination. So through the whole route, the source IP address remains PC4's IP address, 192.
So throughout the entire process, the source IP address and the destination IP address never change. So then how does that work when it jumps between all these different IP addresses? Interesting.
168.4.1. Okay, for this video, there will once again be supplementary materials to help you practice what you've learned. There will be a packet tracer practice lab, in which you use packet tracer's simulation mode to analyze a packet and test your knowledge and understanding. That will be the next video.
Simulation mode always kind of blows my mind.
And that's it. There won't be a flashcard deck for this video, since there wasn't actually any new information in this video. However, if there are some new points that you picked up in this video, feel free to make your own flashcards.
This was a good one.
Actually, even though I make flashcard decks for each video, I also think it's a good idea to make your own flashcards too, if there is anything else you want to remember. You can also edit the flashcards I provide, or delete some flashcards if you think some of them are not necessary. The flashcards are just a tool to help you, so feel free to use them however you think is best. Okay, that's all for today's video. Good luck with your studies.
Yeah.
Thank you for watching.
This one was a really good one. It really kind of connected the dots.
I am preparing for security analyst, so I need to also learn this.
Go for it, man. Yeah.
Welcome to Jeremy's IT Lab.
You should subscribe to Jeremy Tech Lab. He's really smart. He's taught me a lot. All right. So let's look at this bad boy. We're going to have to do a lot of things. Here, can we... Are they now connected? Yeah, they are. Good. All right, there we go. We're good. We're good. All right, let's check this out.
This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. Also, remember to download this Packet Tracer Practice Lab from the link in the description. This lab will be a little different. You won't actually be doing any configuration. However, you will be testing your knowledge of what was covered in Day 12's lecture video in a hands-on environment. This is essential knowledge to have a basic understanding of how a packet travels from source to destination. So, there are 3 main questions here, 1, 2, and 3. You're asked to identify the source and destination MAC addresses used as a packet travels between different points in the network. Let's get right on it with question 1. Question 1 says, PC1 pings PC4. Okay, PC1 is here in the 192.168.1.0/24 network, and PC4 is in the 192.168.3.0/24 network.
Yep.
We are asked to identify the source and destination MAC addresses at each specified point in the route to PC4. Just an aside, remember that the source and destination IP addresses will never change. The source will be PC1's IP address of 192.168.1.1, and the destination will be PC4's IP address of 192.168.3.1. We are told to identify the MAC address by identifying the device and interface. To avoid clutter, I didn't write out all of the MAC addresses for each device and interface, so we'll just say R1G00, for example, instead of the whole MAC address. I'll then show you the CLI commands to verify the MAC address to check your answers. Okay, so part A of question 1 asks the source and destination MAC addresses at the connection, or the segment, between PC1 and switch 1. Well, let's think about this. Because PC4 is located on a different network, PC1 will encapsulate the packet with an Ethernet header, and the destination MAC address will be the MAC address of its default gateway.
Yes.
In this case, that is R1's G00 interface. So that will be the destination MAC address.
Okay.
How about the source? Well, that will be PC1's MAC address, since it just sent the frame. How about B, the source and destination MAC at the switch 1 to R1?
No, I'm saying yes to, like, I'm understanding this. PC1's trying to send to PC4 over here. So that means that its source IP is going to be 192.168.1.1, because that's the address for this. And its destination address is going to be 192.168.3.1, because that's its destination. It knows that this PC is outside of its network, so therefore it's going to send the packet to its it's going to send it to its default gateway, which is 192.168.1.254, and it's going to ask for its MAC address, and its MAC address is going to come back. Yeah, Texas in the United States. Although since I'm a Texan, I believe that Texas is its own country. It's a little thing. There you go. Have a little knowledge about Texas. We have to travel to the Alamo once a year. Anyway.
1 segment. Well, it should be the same as in A.
Donald Drum.
Really?
No, it's a joke. You don't actually have to go to the Alamo once a year. That's just another Texas joke, because you should always remember the Alamo. Always remember the Alamo.
Switch 1 won't actually change the source and destination MAC addresses in the frame. It will simply use the source MAC address field in the Ethernet header to learn PC1's MAC address if it doesn't already know it.
It's one of the biggest states.
And then forward the frame to the proper destination, or flood it if it hasn't learned the destination MAC address yet. So, let's confirm these first 2 answers using the CLI and Packet Tracer simulation mode. First, though, I'll send a ping from PC1 to PC4 just to allow the ARP and MAC learning processes to complete, so we can just view the ping packets in simulation mode. I'll hop on PC1. So, enter the CLI of PC1, and let's ping PC4. Ping 192.168.3.1. You'll notice...
No, Texas is a state. It is a state. It used to be a country. We were our own country. We won our independence from Mexico. And, oh, shit, I should know this. 1824? Hold on. I have to know this. When did Texas get its independence from Mexico? 1836. I was close.
Sorry, bro.
No, no, it's fine. My brother would be very upset with me if he knew that I forgot that. 2.3.1. Let's check it out. So we're pinging in the data.
Notice that when you first issue the ping command, not all of them are successful. This is because all of these devices have to finish their ARP process, and the pings time out while that is happening. Also note that in a Windows PC, when you use the ping command, by default, 4 pings are actually sent. Now let's send another ping. Hit the up arrow to repeat the command.
Wow, so that's why things time out, is because it's doing all the ARP requests. But then once it has all those, it goes, and that's why it sends 4. Wow. And that's why even if you get 4 deads, like you should probably still do it at least one more time just to make sure. That's crazy. Now, dude, Texas is huge. You can drive 8
Bro,
hours.
I am from Iran.
Oh, nice. You can drive 8 hours in almost any direction in Texas and still be in Texas.
Enter it, and there you go. All pings are now successful. Now let's also check the MAC addresses of PC1 and R1's G00 interface first.
India.
On a Windows PC, use this command.
Okay.
ipconfig/all. Scroll up here for the
ipconfig. /all. Invalid command. Oh, there's... I get confused when there's supposed to be a space. And now we have all of our information all right here. Okay.
Fast Ethernet 0 interface and check the physical address here, which is the MAC address. Okay, let's just remember these last 4 digits. So PC1 is 1111. How about R1? Let's check. I'll hop on R1. Enter privileged exec mode with enable, and you can view the MAC address of the interface with this command. Show interface G00. Scroll up here, and it says hardware is gigabit Ethernet. Address is 0000.0.
Show interface. Show interface. Interesting. See here. Show interface G0
What
slash.
is your name, bro, and why your channel name is so dirty?
So my name is Tyler, and that's where my other channel is, Tyler Lamont. The reason my because it looks like you're probably on ParaDiddlePete. My channel was originally about music, and I was an orchestral percussionist. And a paradiddle is something called a rudiment. So a rudiment is like a series of patterns that you play. So a paradiddle is actually right, left, right, right. So that's what that is. Where is the... Oh, here it is.
Zero 01AA.AAAA. Again, let's remember.
Oh, really? I didn't know that. Le Monde is actually French. It means the world. Le Monde.
Remember those last 4 digits. So R1's G00 interface is AAAA. However, let me point out one more thing. Next to this MAC address, it says BIA, followed by a different address. I said in one of my lecture videos that BIA, or burnt-in address, is another word for MAC address. So what's up? Does this interface have 2 different MAC addresses? Well, the burned-in address is the actual MAC address assigned to the interface by the device maker, in this case Cisco, when it was made. However, you can actually configure a different MAC address in the CLI, and it will use that one. That's what I did in this case, to make it easier to remember. Let's check out that command to configure the MAC address. Show
Sorry
running
for being
config.
rude.
Scroll down to gigabit Ethernet 00.
No, you're good, dude.
And there it is. MAC-address.
Oh,
But
whoa.
it says
Yes.
really.
Scroll down to gigabit. Let's check out that command to configure the MAC address. Show running config.
Show running config. Ooh, there it is. There it is.
Scroll down to gigabit Ethernet 00, and there it is. MAC-address, followed by the MAC address you want to configure. Okay, so the last 4 digits of PC1's MAC address are 1111, and for R1, they're AAAA. Now let's actually confirm by using simulation mode. Click on simulation mode in the bottom right here, then let's go to PC1 again, and send that ping once more. Ping 192.168.3.1. Here's the ICMP packet, and I'll hit this arrow once, so it is sent to switch 1. Let's check the source and destination by clicking here to analyze it. Look at the in layers. This is the frame as it is received by switch 1. Layer 2, Ethernet header is from 1111, which is PC1, to AAAA, which is R1's G00 interface, just like we said. Notice the layer 1 info here too.
Why is it not doing it? Hello?
How long you are going to study, bro?
Probably until about like maybe 10 a.m. my time. I don't understand why mine didn't do the thing. Oh, it did do the thing. Ah, I did it. Here it is. Yeah, probably until about 10 o'clock my time. So like another 40-ish minutes or so. Unless I finish this
Showing
early.
the physical interface it was received on. Now on the right here, out layers,
In my time
is the
it's
frame as it
PM,
is sent
so it's
from switch
time
1
for
to
bed.
R1. Notice the layer 2 info is the same, from 1111 to AAAA. This time you can see Gigabit Ethernet 01 in the layer 1 info here, as it will exit out of the G01 interface en route to R1. So that's A and B. I'll close this here, and I'll just press this once more so it is sent to R1. Now let's move on to C. What are the source and destination MAC addresses at the R1 to R2 segment? Although the source and destination IP addresses will remain the same, as R1 encapsulates the packet with an Ethernet header, it will use the MAC address of its G01 interface as the source, and the MAC address of R2's G00 interface, which is the next hop in the route, as the destination. Let's check their MAC addresses to be sure. I'll hop on
Come
R1
back
once more.
tomorrow, will you?
Show interface.
Study streams are on Monday and Wednesday at 8 a.m. And then there's a review session on Sunday at 8 a.m. All my time.
G01. Okay, the last 4 digits are BBBB. Now let's check on R2. Enter privileged exec mode with enable. Next, show interface G00. Okay, the last 4 digits are CCCC. So the source should be BBBB and the destination CCCC. Let's check. The packet is here at R1 now. I'll click on it. Now let's check the right side, the out layers, which is the packet as it is forwarded out of R1's G01 interface. You can see the source MAC of BBBB and the destination MAC of CCCC. Perfect. Okay, I'll exit out of here and click this arrow once more to send the packet to R2. Okay, now here the explanation is similar to the last step, so let's just skim through it. The source should be the MAC address of R2's
Okay, this is
G01
starting to make
interface,
sense.
Believe that I am
and the
only
destination
viewer
should be the
for
MAC address of
the fourth
R3's
time.
G00 interface. Let's go back to the CLI of R2 to check the MAC address. Show interface G01. Okay, the last 4 digits are DDDD. Now let's go to the CLI of R3. Enter privileged exec mode with enable. Next, show interface G00. The last 4 digits are EEEE. Okay, let's check our answer.
Okay.
Click on the frame here, and again, let's look at the out layers. You can see the source of DDDD and destination of EEEE, just like we predicted.
But I have to
I'll
leave,
exit this
bro,
frame
sorry,
here,
bro,
and then click the arrow again to send it to R3. Next, how about E, the source and destination MAC between R3 and switch 2?
Later, man.
Well, at this point, the destination IP address is
Have a
part of the
good
network
night.
connected to R3, 192.168.3.0/24. So R3 knows it can send the packet directly to PC4. So it will set the destination MAC address to PC4's MAC address and use its own address as the source. So actually, the answers should be the same for part E
Good
and
night.
F of this question. So I'll send the packet forward once more, so we can check the in and out sections at switch 2. Okay, let's check the MAC addresses first. I'll go back to the CLI of R3. Let's check G01's MAC address. Show interface G01. Okay, the last 4 digits are FFFF. How about PC4? Let's click on PC4, click on desktop, then command prompt, and do you remember the command? It's ipconfig/all. Scroll up to the Fast Ethernet 0 interface, and here's the physical address, the MAC address. The last 4 digits are 4444. Okay, so for both E and F, the source should be the MAC address ending with FFFF, and the destination should be the MAC address ending with 4444. Let's click on that packet here. And notice that in both the in layers, which is the frame as it is received on G01, and the out layers, the frame as it is forwarded to PC4, the source MAC ends with FFFF, and the destination MAC ends with 4444. So we were correct. So that's all for question 1. I'll exit simulation mode for now. Question 2 is shorter, involving a ping from PC1 to PC3, which is on the same network. The big difference here is that, since the destination is on the same network as the source, PC1 won't send the packet to its default gateway. It will send it directly to the destination, PC3. Also, although switch 1 is in the middle, remember, it won't change the source or destination MAC addresses itself. It will simply forward the frame to its destination. So both A and B should have the same answer. The source should be PC1's MAC address, which if you remember is 1111, and the destination should be PC3's MAC address. Let's quickly check PC3's MAC address. I'll go on the CLI of PC3, and now let's use that command once more. Remember, this is a command for Windows PCs. ipconfig/all. Scroll up to the Fast Ethernet 0 interface, and here's the MAC address. The last 4 digits are 3333. Okay, now before checking, I'll ping from PC1 to PC3 just in case, to let the ARP and Mac learning processes complete. Ping 192.168.1.3. Okay, now let's go into simulation mode and ping once more. Click on simulation mode in the bottom right, return to PC1, and let's ping. Ping 192.168.1.3. I'll click the arrow once to forward the packet to switch 1. Now let's check it. As you can see,
that's what the
as the
arrows
packet comes
do.
into switch 1 via F01, and as it exits via F03, the source MAC is PC1's, ending with 1111, and the destination MAC is PC3's, ending with 3333. Okay, that's all for question 2.
Source and destination MAC
Now, as for question 3, I want you to post your answers in the comment section of this video.
Okay, so earlier in the stream, I talked about how I didn't understand why there had to be 2 different numbers. Like, why are there MAC addresses and why are there IP addresses? Like, why would it not be more simple and more like efficient to have just one number? This is why we have 2 numbers, because we have to go through all of these different hops, and every single one of those hops needs to have its own number, and that number is assigned to the port. And we're mainly focused on the IP address, which is a public IP address. Well, it doesn't have to be. I don't want to put it like that. And then we have the MAC addresses, because you could have the same IP address come back. The chances of you having the same MAC address coming back, probably not right. I don't know. Maybe I still can't explain that correctly.
I will leave a pinned comment down below with the questions, but it will be in the same format as for question 1, but in reverse order. Leave your answers by identifying the device and interface. For example, the MAC address.
Bro, it went really well. I passed that test and I got a job. And now I'm trying to get my CCNA so that way I can get a better job. So it went really, really well. I hope that everything's going well with you, and that I don't know if you were trying to take your test or whatever, but I hope that it went well for you.
Of R1's G01 interface. You don't need to enter the actual MAC addresses of the interfaces. Okay, looking forward to your answers. That's all for this lab. Thank you for watching.
Okay, that was a really good lab. I know we did a lot of stopping and stuff, but basically it boils down to this. We went into here. I don't know why that's frozen. Okay.
Well done, man. I'm writing AZ104 in about a week.
Nice. I don't know what that is. Writing AZ104 in about a week. Is that a test? Can I Google that? What is AZ104 certification? Oh, it's the Microsoft administration. Oh, yeah. Yeah, I've looked into this one. I'll probably end up getting some type of Microsoft or something certification, because it's like really, really good to have. A lot of jobs and a lot of applications that I've looked at have requested for that. Yeah, I didn't know it was called the AZ. That makes sense. Azure administrator. Wow. Cool. Good for you, dude. I hope it all goes well for you. Can I...
Working my way up in the cloud security path, crossed fingers, medium light skin tone.
Nice, dude. Oh, is this frozen because I had froze it? Okay, so now let's ping. Let's move it. And then we can click on these. Okay. Yes, it's all starting to make sense. So here's the layer 1 port. Here's layer 1 port. Here's our Ethernet headers. Here's the number that we were really needing to look at. Okay, this is all making sense. Okay. I feel like the last two videos have really like helped me understand a lot of core concepts. This has been really good. We have a little bit of time left. So, honestly, what I really want to do is the lab from yesterday. I don't want to do the troubleshooting one. I want to do the one where we make it ourselves. Okay. Okay, I guess we are not zooming in for some reason. So what we need to do is that we need to configure the PC and the route according to the network diagram, host names, and all that stuff. So we're going to go to PC. We're going to go to default gateway. Our default gateway is going to be 192.168.1.254. And then, yes, interface. Then our IP address is going to be 192.168.1.1, and that should make our subnet mask. It did. Okay, and again, the reason why this is 255, because it's about how many bits have been used. Because it's /24, and these are all octets. 8 plus 8 plus 8 is 24. That's why it's 255. I hope that makes sense. If it doesn't, let me know. Okay. Then we need to go here. Enable and config T, hostname R1. Then we're going to, we need to set the IP address. So interface G0/1. No, IP address. IP address 192.168.1.254. 255.255.255.0. Yes. And then we need to set no shutdown. Do show IP interface. Okay, good. Internet protocol disabled. Okay, that's correct. Oh, we talked about that a few days ago. There is something else. Oh, brief. Yes. So now we need to do the same exact thing, but for G0/0. So we're going to go to interface G0/0. Yes. And then we're going to go to IP address. IP address is going to be 192.168.12.1. 255.255.255.0. Yes, no shutdown. Okay, that should be the basics of it. Now, if we do... Yeah, okay, this is down because I haven't done this yet. Okay. Let's do the same thing with this one. This is good practice. Enable config T host name R2 IP address 192.168.12.2 255.255.255.0, and I know that because of the side R that's right here. Why is that invalid? Because I'm not in the interface. I'm still in IP config. That's why. So interface G/0/0. Now we want to do IP address. No shutdown. Yeah. Okay, now we're going to go to interface G0/1. And we are going to enter in IP address 192.168.13.2. Oh, because I did 12. There we go. No shutdown. And then let's see. Do show interface config brief. No IP interface brief. Okay. Okay. We're doing good. Okay, and just so you know, if we went here and we did it again. Did I not do... No way. Oh no, I just haven't done this one yet. Okay, never mind. I thought I just screwed up. Config T. Interface G 0/0. No shutdown. IP address 192.168.13.3. I don't know, it just popped up. Something just popped up and it went away. Whatever, I guess. Okay. So this is now going to be the IP address, or what we're going to use. It wasn't a pop-up. It was a video or something that a video. It's like I have my stream stats or whatever, and it like it's just really behind. Anyway. Ooh, IP address 192.168.3.254 255 oop 55.255. Dang it, dude. My fat fingers. And I already did no shutdown. Oh, let's exit. I forgot to change the name. Host name R3. Okay. And then let's do show IP interface brief. Oh. Okay. So I need to go back into interface G0/1. No shut down. Okay. We're good. Let's go here, desktop, not command, config. Default gateway is going to be 192.168.3.254. Our interface, our IP address is going 192.168.3.1. Okay. So that did one. That configured all of that stuff. But it didn't configure the static routes. Okay. Which shouldn't take... That's weird. Shouldn't take too long. Yeah. Okay.
Welcome to Jeremy's IT Lab. Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment. Now, let's get to the main point of this lab.
Yes.
Configuring static routes. Before starting, let's think about what static routes we'll have to configure. We need two-way reachability, so PC1's ping can reach PC2, and then PC2's reply can reach PC1. R1 is already connected to the 192.168.1.0/24 network, so it just needs a route to 192.168.3.0/24. Likewise, R3 is already connected to 192.168.3.0/24, so it just needs a route to 192.168.1.0/24. R2, however, is not connected to either of those networks, so it will need routes to both. So that means a total of 4 routes need to be configured, 1 each on R1 and R3, and 2 on R2.
Okay.
Let's go on R1 and configure the first of the routes. We have to be in global config mode.
Okay, so I'm trying to think. I think because what I'm struggling with is the command. I'm pretty sure it's IP route, the IP address, the net mask, and then its destination IP address. I'm pretty sure that's it.
So I'll type exit to get out of interface config mode. Configure the route with this command, IP route, and let's use the context-sensitive help to check the options. So it says destination prefix, meaning the network address, which is 192.168.3.0. Use the context-sensitive help again, and next is the mask, which is 255.255.255.0, since it...
Okay. Point 3. It's the destination and then the source.
It's /24. Next, we can specify the forwarding router's address, which is the IP address of the next hop router, or we can specify the exit interface. All of these options are interface types. I'll specify the next hop address of R2, which is 192.168.12.2.
Okay. So I was kind of right. So we need the destination, which is 168.3.0, because that's the network. Here's the mask, because it needs that. And then our next hop, which is going to be 192.168. 192.12.2. Yes. Which means, okay, I'm just going to try to do this with R2. Okay. We're going to do IP routes. Our destination is 192.168.3.0. And then our next hop is 192.68.13.3. But then we also... Ah, crap. So did it just automatically kick me? Look at this. Did it automatically kick me to out of the interface? Because I don't know. This might have screwed things up. We're gonna find out. Okay, so then the next thing is I need the route. Do I just put it in again with this IP address instead? And then the next route is 12.1. Shit. Okay, we're going for it. Let's see if we were right.
If I use context-sensitive help again, you can see there is another possible option, distance metric for this route. I'll talk about this option in a later video, but this CR down here means we can just enter the command as is. Okay, now let's check out R1's routing table. Do show IP route.
I didn't look this up.
There's the static route we configured, as indicated by the S here. You can also see the configured and local routes for R1's two interfaces. Remember, the local route is the actual address configured on the interface with a /32 mask, so it specifies just that single address. And then the connected route is the network address of the network the interface is connected to. Okay, R1's route is done. Let's go on R2. Again, exit to get out of interface configuration mode. Let's configure the route to 192.168.1.0/24. IP route 192.168.1.0, 255.255.255.0.
Okay, I did that.
And then just to practice the other option, I'll specify the exit interface instead of the next hop IP address.
Okay,
G00.
because you don't have to put the IP address.
This message comes up, but you can ignore it.
interface.
It says, if not a point-to-point
Because the IP address is the interface. They're one and the same.
interface. However, this is a point-to-point interface, meaning it connects only to one other device. This is different than, for example, many routers connected to a single switch, which we would call a shared segment. Anyway, don't worry about that for now. You can just ignore this message. Okay, next let's configure the route to 192.168.3.0/24. IP route 192.168.3.0, 255.255.255.0, and this time let's do the next hop IP address, 192.168.13.3. Okay, let's check the routing table. Do show IP route. Okay, here are the two static routes, and the connected and local routes for each interface. Looks good. Finally, let's configure R3 static.
Okay. Doing good. Okay. Exits. IP routes. Our destination. Our destination is 192.168.3.0, 255.255.255.0. And our next hop is going to be 192.168.3.1. I want to double check that.
Static route. Type exit to get out of interface config mode, and let's configure a route to 192.168.1.0/24. IP route 192.168.1.0, 255.255.255.0, 192.168.13.2, setting R2 as the next hop. Let's check the routing table.
Oh, okay. See, I'm glad I stopped that. Because we need to be able to... Okay. I understand. Because it's already connected to the switch. We don't need to statically put it. We just have to go backwards. So that is why our destination is actually 1. And that this is actually 13.2. Because that's this guy right here. That should be it.
Do show IP route. Okay, looks good. 1 static route and the connected and local routes for each interface. Now let's go on PC1 and try out that ping.
If this
Click on
doesn't
desktop,
work,
then
it's
command
because
prompt.
I messed up that one
Okay, so
command.
this is the moment of truth. The first ping might fail due to ARP, Address Resolution Protocol, but once ARP is finished, the rest of the pings should work if we configured everything correctly. Let's try. Ping 192.168.3.1. Okay, looks like PC1 is able to reach PC2, and PC2 is able to reach PC1 with its reply. We have successfully configured static routing. That's all for this lab. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. That's all for now. Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe.
That means that command that I like screwed up, that means that was a big deal, and I would have to go back in and fix that. Yeah. Unless no. So I bet you anything it happened when I screwed up that interface with that. There's no telling what I did or how to undo it. It might just be as simple as no, adding no in front of the command. But we'll try it again later. This was just practice. All right. If you haven't already, you should subscribe to Tyler Lamont. I do study streams every single Monday and Wednesday, and I do study stream or review sessions on Sunday, where we're not going to watch a video or anything. We're just going to kind of review. Okay. If you haven't already, you should definitely subscribe to Jeremy's Tech Lab. He does amazing things. You should definitely go and check him out and look at his channel. It's great. It's definitely really good. I use his videos all the time to help learn. I have some videos of my own. If you want to go check them out, you can. And then you can check out past VODs that are there. This is the lab review that we're going to do. We're going to do a lot of packet tracers and some Anki flashcards, which I know everybody loves the Anki flashcards. Not really. I absolutely hate them, but they're really, really good. Okay. Anyway, so that's what's going on. I hope you enjoyed it. I hope you learned something. I am out of here. Have a wonderful day. Oh, and remember, build with what you got. Work with what you got. Build what you need. See you on Sunday.